We'll start with the first talk, which I think is Simone Gallarati. Simone is a postdoctoral fellow shared between the Sigman Lab, University of Utah, and the Doyle Group, UCLA, funded by a postdoc mobility grant of the Swiss National Science Foundation and by the NSF Center for Computer-Assisted Synthesis. His research is focused on developing and applying data-driven computational tools to optimize and understand chemical reactions. So I will stop sharing my screen and I welcome Simone to start his talk.
Wonderful. Thank you very much. Let me share my screen. Yeah, wonderful. Thank you very much. As Gabriela said, my name is Simone Gallarati. So I'm a postdoc and I'm actually shared between UCLA, the Doyle Lab, and the Sigman Lab at University of Utah. And then the work that I'll give you a little brief overview of was funded by the SNSF and by the Center for Computer-Assisted Synthesis. And for those of you who may not be familiar with CCAS, so CCAS, as I said, is the NSF Center for Computer-Assisted Synthesis, and the objective of CCAS is to revolutionize the way that we discover and optimize chemical transformations. So CCAS is funded on 3 pillars or themes, which are data, of course, experimental data, representation, specifically the way that molecules and chemical reactions are encoded in a machine-readable way, and algorithms, that is the way the data is processed as a function of the representation. And then our work at CCAS is constructed around 4 thrusts. And specifically, our work in the Doyle and the Sigman Lab has been focused on the optimization of asymmetric transformations. And specifically, our contribution has been to show that injecting mechanistic information into machine learning models of enantioselectivity not only improves the accuracy of those predictions, but also extends their domain of applicability. And that I said, we've been specifically focused on applying and developing these models for asymmetric catalysis. So here are some of the typical challenges that we face in asymmetric catalysis in organic chemistry. So if you take, for example, this nickel-catalyzed cross-electrolyte coupling reaction developed by the Doyle Lab. So the way we typically optimize a transformation such as this one is that we select a combination of model substrates, and then we screen a variety of chiral ligands to identify the one giving the highest possible enantioselectivity expressed as EE. And then after we've identified a chiral ligand such as this one, we take that ligand and we use it to evaluate the substrate scope of the reaction. And unfortunately, something that happens quite frequently is that once we evaluate the substrate scope, we find a combination of substrates that performs less well than the model substrates with that same quote-unquote optimal ligand. And then an even more challenging situation is that when we're developing new reactions, for example, if we identify a chiral ligand for a specific transformation, for example, this arylation of benzyl chloride, and then we use that same ligand for a different substrate class, so for example, for this vinylation reaction, then that same ligand that was optimal for a previous transformation might not be the best one for a new reaction. And of course, this limits our ability to transfer knowledge from one reaction class to another. So how can data science help with these challenges and to address these objectives? Well, in principle, we would like to have machine learning models of enantioselectivity that allow us to make predictions on unseen ligand and substrate combinations, and also are transferable from one reaction class to another that help us sort of cold start the optimization of new transformations. The issue that we face as data scientists is that we often only have very sparse data for training. And this concept of sparsity of data is something that I will go back to, that it's quite important. So we often only have knowledge of very few combinations of chiral ligands and substrates across different transformations. So the way we approach this problem is that we wanted to leverage mechanistic information, specifically the knowledge of the potential stereodetermining steps in a transformation and a reaction, to construct a reaction representation that would allow us to train machine learning models that are applicable to different reactions, and so would be transferable and allow us to extend their domain of applicability. So how did we do this? As I said, we want to leverage mechanistic information, specifically the identity of the potential structures involved in stereoinduction. So we know a little bit about these nickel-catalyzed cross-electrified coupling reactions that have been proposed to proceed through two potential stereodetermining steps, specifically the capture of an alkyl radical by a nickel-2 species to give this nickel-3 intermediate, and then subsequent reductive elimination. And either of these two steps have been proposed to be stereodetermining. So our objective was to construct reaction representations by taking features from these computed structures. Both the radical capture, the intermediate, and the reductive elimination transition states, because they encode both the ligand and the substrates involved in the reaction. Now, of course, to be able to do this, we need to have access to a computational workflow, a pipeline that gives us access in a reasonable time frame to these fully optimized structures and their corresponding features in a way that is compatible with high throughput screening. And this is the workflow that we have developed. I will not go into the details, of course, for the sake of time, but it is described on our GitHub and in our recent publication. But essentially, this workflow comprises two steps. The first step is the automated structure generation from a library of ligands and template structures for the different stationary points on a potential energy surface. And then the second step is these high throughput quantum chemical computations when we fully optimize these transition states, the ensembles, so conformational ensembles on these transition states, and then we extract features and we use those features to construct our reaction representation. So we've applied this workflow to a number of case studies, and the first one that I want to highlight again is going back to this concept of the sparsity of data, where we look at the combination of ligand screening. So we have a fixed combination of model substrates where we evaluate multiple chiral ligands, and then substrate scope where we fix that chiral ligand, and then we evaluate multiple combinations of substrates. So we have this sort of matrix, which often for organic chemists look like this. So we kind of this T-shape, and we use only that data for training our machine learning model. And then we want to make predictions on unseen combinations and even unseen ligands. So specifically, we focused on a combination of substrates that had previously been reported in lower enantioselectivity with the so-called optimal ligand. And then by training our machine learning models using features extracted from those structures, so from the species on the potential energy surface that are proposed to be involved in stereoinduction, we were able to identify an unseen ligand that gave a moderate improvement in enantioselectivity over the previously identified best ligand. In another case study, we wanted to kind of push our approach even further and then see if we could train machine learning models on a set of reactions and then transfer that information to an unseen combinations of different substrate classes. So we took data from the literature on nickel-catalyzed cross-electrified coupling reactions involving sort of a matrix of different CSP2 electrophiles and CSP3 electrophiles. And again, this is a situation of this data sparsity because we have only tested some ligands for some combination of substrates, so we don't have the full combinatorial matrix. And we use that data to train our model. And then once we trained the model, we applied it to a different transformation. So this is a CSP3 coupling that involves one electrophile that is already being seen by the model and a different electrophile that is completely unseen. So this is, of course, quite a challenging situation because we're asking our model to extrapolate significantly but we wanted to kind of push this approach as much as possible. So our model actually gave good out-of-sample predictions on this transformation, and then most importantly, it was able to identify a ligand class that was best performing in this reaction. And I want to emphasize this because this particular ligand class was entirely unseen in the training data. So this particular type of ligand had not been seen by the trained model. And so this concept where we can take literature data, train a model, and then use it on a different reactions is quite exciting because it suggests that we can sort of build these models to so-called cold start or warm start the optimization of a new transformation. And this is what we did in our last case study, where we sort of tried to do this prospectively for an unreported asymmetric reaction. So another nickel-catalyzed cross-electrophile coupling reaction, where we combined our featurization strategy with active learning, specifically EDBO+, which is the Doyle Labs Bayesian optimization platform. So our workflow, our featurization strategy allows us to use all of the relevant transformations from the literature as a way to pre-train our optimizer, specifically our GPR model. So we can do that, train on a model, and then use it in this active learning strategy where we use Bayesian optimization to sort of survey the ligand space and explore it and exploit it. And then by doing so and performing only a minimum number of experiments, we were able to identify a ligand class that was promising for this transformation. And of course, this was possible by the efficiency of our featurization strategy, where we were able to generate this virtual space and then extract features from, all sort of ligand and substrate combinations. And I want to emphasize that we had previously tried to optimize this reaction with a more traditional approach, where we sort of surveyed a variety of ligand classes, identified a hit in specifically the Biox class, and then tried to synthesize a large variety of Biox ligands. But even after having made more than 50 ligands, we could not get, a significant improvement in enantioselectivity. And then the optimizer, after just a couple of rounds of experiments, moved away from the Biox class and then identified a different class, specifically Piox ligands, that were, giving small improvements in enantioselectivity for this reaction. And I'm not sure how I'm doing for time, but just for the sake of leaving some time of questions, I will finish here. So I want to thank the two groups that I'm a member of. So the Sigman group at University of Utah and the Doyle Lab at UCLA. And then this work has been actually a collaboration also with the Risman Lab. And as I said, it was funded by CCAS and by the SNSF through a postdoc mobility grant. And then I have a personal tradition that I always finish all of my presentations with a quote of the day. So I'm just going to give you my quote, which is taken by a play, Arsenic and Old Lace. And the quote is, "Oh, Mortimer, don't be so inquisitive. The gentleman died because he drank some wine with poison in it. We put it in wine because it's less noticeable. When it's in tea, it has a distinct odor." And with that, I thank you for your attention, and I'm very happy to take questions.